Okay. Hi. Hope your spring break went well. So today starts the last part of the class, which I'm excited about. So we're done with spring break. We only have one more topic left. So the rest of all the lectures will be mostly about sorting. There will be a couple of optional software engineering lectures, which are kind of fun. So stop by. But sorting is the last major topic we have to do. We're done with all the data structures, which is great, I guess, except these topics, which I forgot to cover before spring break. So I'll do these, and then we'll be fully into the sorting unit of the class. Fun. Okay, so before spring break, I told you all about the trie, which was this character by character data structure, which is used to store sets or maps of strings. So this is being used to represent a set of strings. I could also use it to represent a map of strings. And we said that tries have really good performance, constant time performance. But maybe that's not so impressive because binary search trees also had logarithmic performance, which is pretty good. And hash tables had basically constant time performance. So what was the point of showing you this special purpose data structure if the runtime isn't that much better than the other set and maps that we've seen? And so what we said, and the cliffhanger that I left you on before break, is that tries are often really good at specific string operations that binary search trees and hash tables are not very good at. So just looking at the pictures, hopefully the pictures can kind of convince you that, let's say I wanted to do something like, please tell me all of the words that start with SA. So in my set of words, there are lots of words. Some of them start with S, A, followed by other letters. So try doing that in a hash set. I have this hash set. It's got all these buckets. Where are all the words that start with SA? Well, they're not necessarily in the same bucket. Who knows what hash code I used to spread these items among the buckets? So here, there's a word with SA. It's like in bucket 0, and then there's another one in bucket 3, and another one in bucket 2. So it's all over the place. To find all the keys that start with SA, I'd have to scan through all of the buckets. And so it turns out the hash table is kind of a piece of garbage for this particular operation. And same thing with the binary search tree. Well, okay, well, the root is sad. Ooh, I don't know why the video keeps going up, but I guess complain at me if it does. Okay, so the root is sad, and yeah, maybe there's some like other words that start with sa elsewhere in the tree, but it's not immediately obvious to me how I find all of the words that start with sa. By contrast, this is the punchline. If I look at the trie, well, here, if I'm looking for all the words that start with sa, I know they have to be, I can start at the root, and I can spell s, and I can spell a, and I know that everything else in this subtree has to start with sa. So the trie gives me a very natural way to complete this operation, where the binary search tree and the hash table, they have implementations that would be slower for this operation and probably more complicated for you to write. So that's why I like tries. They're good for specific string operations. Okay, so I kind of hinted at what we have to do. For example, I want to find all the words that start with saw, and in this particular set happens to be those words. And so I will not walk through the entire implementation of this. All the slides are there for your reference if you want, but I just think this is one of those things where if you step through it slide by slide, I think you'd get the hang of it pretty quickly. So I won't belabor the point in lecture, but the high level idea is somehow I can do a traversal to get all of the keys in this set. And I can also use a traversal to get all of the keys that start with SA. So I guess as a bit of a warm-up, what kind of traversal should I do to get all of the keys? So here's my trie, and I want all of the words that are in the trie. So what kind of traversal could I do? Well, maybe consider something like, and I know the words, there's a lot of words, but it's kind of like a depth-first traversal. So I start at the root and just kind of watch where this call help depth-first search helper is going. So it starts here, it goes A, which then calls W, and then calls L, and then calls S. Okay, great. And now I found a word alls because this node is blue, and then I return, okay, and then I return all the way back up. I get A, okay, great. I go over here and I do another depth first search. So S calls A, and then and so on. And so it's kind of a depth first search. You have to do a little bit of extra bookkeeping. That's what all this other stuff is. So you have to keep track of things like, what are all the letters I've seen so far? And I can use an extra argument to help me keep track of that. But at a very high level, hopefully it feels okay that doing a depth first traversal will give me all of the keys in my try. So I start here, I go depth first, I see A is blue, so I spell the word A, WLS, I spell alls, and then I return back up, and then I do the same thing on the right branch of the tree. So basically a depth first reversal, but with a bit of extra bookkeeping to remind myself the letters that I've seen so far. And that lets me get all the words. Okay, so that's how you would get all of the keys, but what if I only want the keys that start with SA? Remember, if I do a depth first reversal starting at the root, I get all of the keys. If I just want some of them, well, then what I can do is I can say, well, I only want the thing starting with SA, so I'll go S, A, and then I'll do a depth first reversal starting at this A node and looking at everything underneath the A. So again, it's a little bit high level, but hopefully it feels convincing that this is an operation that the try would be very good at, while the binary search tree or the hash table would kind of struggle at doing this. Okay, questions? I just realized I should probably check Zoom periodically today. The white node, I'm assuming maybe you mean the one at the top, that's the root. You use that to indicate that nothing has been spelled yet. Good question. Okay. So I will briefly tell you about some applications of this. I don't expect you to know this in a lot of detail, but might as well. So we saw that I can use keys with prefix to find all of the words that start with some prefix. And you might be like, well, that's great, but when would I ever use this in real life? So it turns out this is very useful in real life, because if you ever go to Google and you start typing in words, you know how it gives you a bunch of suggested searches? Well, how do you think it's doing that? It must be using some form of keys with prefix, where it says, what are all of the search terms that start with how are? And it gives you all of these common ones. So that might be an application of keys with prefix. And this would be a use case if you were building a Google style search engine. That'd be a great case to use a try instead of one of those other data structures that we saw. So I actually won't go through these slides in too much detail. There is a video if you're interested. It's one of those things where I think if you just went through the slides, you'd be okay with it. I also don't think we test you on this in a lot of detail anyway. But basically the idea is if you want to keep track of the most common words with prefix, you can add some extra bookkeeping to say, I don't want just any of the things that start with B, but I want the most common words that start with B, and I can use some extra bookkeeping to keep track of that. But again, not something I'll talk about in too much detail. There's also some fancy tricks you can see to make the try even faster, but we won't discuss, as the slide says. Are people okay with my autocomplete speed run? Are we convinced that this is probably useful for autocomplete? Okay. So to quickly summarize, why did we talk about tries in the first place? Well, theoretically, the performance is a little bit better. I went from theta of 1 with some asterisks to theta of 1 all of the time, which is good. Then I had to think about how to implement the try. And remember, there were a lot of different choices. And if you trusted the abstraction, you believed that whatever was in the box was a way to map characters to nodes, and how the mapping happened was not our concern, then you can swap out implementations and say, maybe I'll use one of those data indexed character maps, a big array. Maybe I'll use a binary search tree. Maybe I'll use a hash table. They're all good choices, although I think the data indexed character map is a little bit more memory inefficient than the other two. And then we talked about just today that tries support very good string operations, or they're very good at supporting certain string operations like keys with prefix that other implementations of a set or a map would not be great at implementing. Okay, so I think this is cool because it shows you that data structures can interact in beautiful ways. We used a binary search tree inside another tree, and we got this beautiful data structure out of it. I think that's nice. Okay, and so although we won't talk about it, you can go look up. There are other types of special purpose sets and maps. If you know that your data type is something special, like a string or a character or a number, well, there are some other data structures out there that are cool, like suffix trees or dog, which is directed acyclic word graph. I just wanted to say dog, but actually not too familiar with what it is. Okay, anything else you want to know about tries, data structures, the entire second unit of this class before we move on to the final unit, which is all about sorting and algorithms? Okay, great. So I'm switching over to the lecture 29 slides for those of you following at home. Let's start talking about sorting. Okay, hope you're excited. So as I said, we are done with phase 2. Here we are in phase 3. So here we go. Okay,
So sorting, what is it? Well, hopefully we've all sorted things before, and so I'll try to make it formal, but roughly speaking, I have a bunch of items. I need to put them in order. And there's lots of different reasons why this would be useful. So I'll try to convince you that sorting is useful, although maybe you already believe it. So remember in the asymptotics lecture, the very first one, we talked about dupe 1 versus dupe 2. And we said, well, if the items are sorted, I can just compare all the adjacent elements to see if there are any duplicates. Well, that would be an algorithm that's a lot faster if the array was sorted. And if the array was not sorted, then dupe 1 and dupe 2 would be a lot slower asymptotically. So sometimes by sorting, you get better algorithms. And if you sort things, you can also build nice data structures. All of this is just to say sorting is a pretty important problem. And so let's go explore different ways to solve it. OK, so I'm going to formally define it. This is kind of pedantic, I'm not going to lie, but it's good to all be on the same page about what sorting is. So I know it's a little bit boring, but let's go through some definitions. So if I have two keys, like A and B, two items of any sort, it has to be the case that A is less than B, A is equal to B, or A is greater than B. It has to be one of those. You cannot have two of these true at the same time. Again, hopefully it's stuff that we're all kind of convinced of, but good to be very clear about it. Hopefully it doesn't seem too wild to suggest that if A is less than B, B is less than C, then hopefully A should also be less than C. So if both of these are true, it means that there is a way to put all of my items in order. And I want my items in non-decreasing order. That is, each item has to be less than or possibly equal to, if I have duplicates, the next item relative to some ordering relation that someone gives me. And again, I know it's kind of pedantic, but just to make sure we all know how to sort things in the same way, that's how we're going to talk about them. OK, here are some examples. And I think, again, some of it's kind of pedantic. But the important thing, I think, on this slide is that sometimes there are different ordering relations you can use to sort something. So suppose I give you this array, cows, get, going, the. Well, you could say, maybe I'll sort this alphabetically. So cows is first, and then get is next, because G comes after C in the alphabet. But there are other ordering relations out there. So maybe I don't want to sort this by alphabetical order of the words. I want to sort it by the length of the words. So that would be a different ordering relation I can use. And if I want to sort by the length of the words, so the shortest words are first, longest words are last, turns out there's actually two valid orderings. I could say the, get, cows going, or I could say get the cows going. Why are there two? Because there's a tie. Both of these have the same length. OK, and so not to get too much in the weeds, I'm just trying to define sorting here. But here's a case where these two words, they're not really equal in the sense that they're not the same word. But under this particular ordering relation, for the sort that I'm doing right now, they're equal in the sense that they have the same length. So sometimes we say two things are equal for a particular sort, even if they are not equal if you think about the Java dot equals method. These two things are not dot equals, but if I use like a dot compare or something, they would be considered equal for my particular sort that I want to do. OK. But kind of a pedantic point, the important thing is, and I guess here's more pedantic points, the important thing is that we want to sort things, we want to put them in non-decreasing order, and sometimes there are multiple ordering relations to do it. OK, are we all somewhat agreed on the definition of sort before I show you something a little bit more important? Oops, sorry, I missed the try question. I'll answer it afterwards. OK, good. So we all know what sorting is and how it works. So now I'll tell you an idea that is more important, which is an inversion. So take a look at this array and say I want to sort it from small numbers to big numbers. So I have 0, 1, 1, 2, 3, 4, 8, 6, 9, 5, 7. Is this array sorted? No, because there are some items that are out of order. So like this 9 should not come before this 5. But is this array like kind of sorted? I think it is, because a lot of the items do seem in the right place. The 0, 1, 1, 2, 3, 4, that was pretty good. And yeah, we kind of messed up with the 8, but it's close. And so if I want to represent the fact that this array isn't sorted, but it's almost sorted, one way that I can say that is I can count the number of inversions in this list or this array. And an inversion is any two elements. So I pick any two elements. They don't have to be adjacent. So I could pick 8 and 7. Well, these two are out of order. The 8 and the 7 are out of order. The 7 should have come first. So that pair forms an inversion. And I can check all of the pairs in this array to see how many inversions there are. And that gives me a rough sense of how sorted this array is. So in this case, there are 55 inversions or 55 possible inversions that could exist because I could check the 0 against any of these elements. Then I could check the 1 against any of these elements. Then I can check the 2 against any of these elements, so on. So if you list out all the pairs, 0, 1, 0, 2, 0, 3, 0, 4, I list out 3, 4, 3, 8, 3, 6. If I list out all of the pairs, there are 55 of them, and it turns out in this particular array, 6 of them are inversions. That is, they are out of order. So for example, we saw 8 and 5. That's an inversion because the 8 should not come before the 5. But out of 55 possible, there are only 6. And that somehow captures the notion that this array is pretty close, but not all the way there. So if I have a definition like inversion, then there's another way to talk about sorting. So I could say, put all the items in non-decreasing order, or I could say, I have this sequence, it has some number of inversions, like 6, and I want this number to go down to 0. So take the items, shuffle them around, move them around, put them in order, such that the number of inversions is 0. It's another way to talk about sorting. But inversions will be pretty useful when we talk about different algorithms, try to convince ourselves that they work. By the way, I will mention now, before we start seeing the actual algorithms, some of our algorithms will take this number 6 and slowly chip away at it, and we'll swap something, and now there's only 5 inversions. And then we'll do another swap, and now there's 4 inversions. So we'll slowly always decrease the number of inversions until we hit 0. That's a valid strategy. Some other sorting algorithms are a bit more wild. They actually shuffle things out of order first. And so the number of inversions will increase at first. You'll actually make things worse when the algorithm starts out, but it's okay because when the algorithm ends, everything will fall in place and the number of inversions will go all the way back down to 0. So sometimes algorithms slowly decrease the number of inversions. Other ones are a bit more wild. They'll increase before decreasing the number of inversions. But all of those are good algorithms that we'll see soon. Okay, so as we talk about algorithms, we should also talk about how good they are. So hopefully the slide, mostly review, but in case spring break has got you, hung over or something, well, let's talk about the time complexity. We've seen that before. It tells us asymptotically how long the algorithm takes to run. And although we haven't analyzed it too much yet, there's also something called space complexity, which tells me how much space the algorithm needs to run. And one thing I'll note that I don't think I've noted yet is that space complexity is usually measured in terms of how much extra space you need. So we don't count the space it takes to store the original array. We only count the amount of extra space that someone would need. Otherwise, every algorithm would have to store the initial problem. So that's a little bit weird. So instead, every time we talk about space complexity, we're not going to count the size of the initial problem. We'll just talk about how much extra space did it cost you to finish running the algorithm. What are the extra temporary arrays or instance variables you had to make to solve the problem? That's time complexity, that's space complexity, all set? Okay, here comes sorts. I will tell you about 2, maybe 3 if I have time. So here we go. I will start with selection sort. Here we go. Here's an array. Do we all agree it's not really sorted? Okay, so here's what I'll do. I'm going to go through the array, find the smallest item, and dump it at the front. And I will do that over and over again until it's sorted. That's it. Find the smallest item, put it at the front, do it over and over again until everything is sorted. So let's scan through this array. Scan. What is the smallest item? 2. Thank you. Okay, so there it is. It's 2. And so I want to move this to the front of the array. Well, at first it might be tempting to say, well, let's take 32 and 15 and let's shift them over and then let's move the 2 to the front. But that might be kind of slow because then I have a lot of these items to shift over. So I will do a clever trick where instead of shifting all the items over, I will just take the 2, I'll just swap it with the 32. So look, 2 was here, 32 was here. They swapped places, and that caused the 2 to appear at the front. That's great. So now if you look at the 2, I'm coloring it gray to indicate the fact that this 2 has found its rightful home. It will never move again. It was the smallest item. We put it at the front. There's no need to look at it a second time. So here's all the stuff that we do have to look at. I scan through it, and I find the next smallest item. So I don't look at the 2. I've already looked at it. It's in the right place. I scan through. Smallest item is 15. Check my work. 15. OK. And again, I have to swap it to the front of the unsorted array. So in this case, it's already at the front. So I swap the 15 with itself, or I don't move it, and it's good. It's locked in place. Will never move again. And now I look at the rest of the array. I scan through. What's the smallest item? 17. Which 17? It's up to you. I chose this one for now, and I will swap it to the front. So the 17 and the 32, they change places. And if I swap to the front, by the way, I mean the front of the unsorted array. I don't want to swap the 17 with the 2. That would not be correct, but I can swap it with the 32. Okay, great. Now it's in place. So I won't bore you with all of the steps, but we'll just keep going. 17 swaps to the front. 17 swaps to the front. 19 swaps. 26 swaps. 32 swaps with itself. 41 swaps with itself. Look, everything is sorted and beautiful. OK, so that's it. That's selection sort. It's basically 2 steps. So do you like it? Do you have a bad feeling about it? Well, I have a little bit of a bad feeling about it. I don't know if you did. And so here is where I started to sense a bit of dread with selection sort. So I started here, and I said, what's the smallest item? And I scanned the entire array to find 2, and then I swapped it. And then I asked, what's the next smallest item? So what did I do? I scanned the entire array again to find the 15. Then I swapped it to the front. What's the next smallest item? I scanned everything again to find the 17. Then I swapped it. So that doesn't feel so efficient. And in fact, you can do some asymptotic analysis and think about how many operations am I doing? How many elements of the array do I have to look at in order to finish this algorithm? So here, I had to look at all n items to find the smallest one. I swapped it. Then I had to look at n minus 1 items, because I don't have to look at the first one again to find the smallest item. Then I swap it. OK, great. Then I look at n minus 2 items, find the smallest one. Then I swap it. Then I look at n minus 3 items. And maybe you see where this is going, n minus 4, n minus 5. Sum that all the way down to 1. And the sum of n plus n minus 1 plus n minus 2 all the way down to 1. Well, we know that's theta of n squared. So selection sort, it works, but it's an n squared algorithm. Hopefully, kind of feels like we can do better. Why were we wasting all the time looking at the same elements of the array over and over and over again to find the smallest item? Imagine if the array had 1 billion items. You'd have to scan through all of them to find the smallest item. And then on the next step, you'd scan through all of the items again, minus 1 item, to find the next smallest item. Seems kind of a waste of time. So that selection sort, it's simple, but maybe we can do better. Thoughts, opinions, questions about selection sort before I pile onwards? When counting inversions, do inversions you decide to do carry out the whole time? That's a good question. I would say for an inversion, someone just hands you an array. It could be sorted, it could be partially sorted, it could be unsorted, and you just count the number of inversions for a specific array. That's kind of how I think about it. So input is an array, output is a number of inversions. OK. OK, good question, though. Sorry for not getting to it earlier. OK, that was selection sort. We saw it, it works, but it's kind of slow. So let's go find something better. So I go back and I think about all of those data structures that I spent all that time learning, and I realized, well, what was I doing in selection sort? I kept trying to find the smallest item. I scan through the array, what's the smallest item? I scan through the array, what's the smallest item? So, and I go back and I think, do I have a data structure that's very good at finding smallest items? Like I give it a pile of data and I say, what's the smallest? Well, yeah, it turns out I do. If you remember the heap or the priority queue, what was a heap really good at? A heap was good at telling you what the smallest item is. That's what the heap was good at. So what if, instead of spending all that time scanning over and over again to find the smallest item, I used the heap to help me find the smallest item quickly? So let's try and do that. So I'll show you a naive version, which hopefully is more intuitive, and then we'll try to make it more efficient. So here's the algorithm, and it's like one sentence. I'll take all my items, I'll shove them in a heap, and then I'll delete the items over and over again and they'll come out in order. That's basically it. We know that the heap will always give me the next smallest item. So if I shove everything in a heap and I pull all the items out one by one, they'll come out in order. That's it. Okay, now I'll try to make it more formal. So while this would work with the min heap, which is kind of how I described it, I will actually use a max heap for reasons that will become more clear in a couple minutes. So trust me on this one. I know how the lecture ends. The max heap will be good. But if you use the min heap, that would be fine. You would just shove all the items in a min heap, pull them out one by one. That works perfectly fine too. Okay, but I'll use a max heap, and hopefully max heap is also okay because I put everything in the max heap and I pull the items out one by one. And in this case, I would get the items from largest to smallest. But that's okay. I can just reverse that and I'll get a sort. Okay, so here I go. Here's my input array. It's our old favorite array. This is our favorite despite the fact that we've only seen it once, but it's our favorite array. We're going to put all the items in a max heap and then pull the items out one by one. So here we go. Here's the items. I will shove them into a max heap. So here are the items. After adding them into a max heap, you get a picture that looks like this. And just to be clear, I don't expect you to instantly see that this is the correct max heap after I add all these items. You'd have to actually run all the steps one by one, syncing some nodes or swimming some nodes as they enter the heap. But I think with enough time and some pencil and paper, you will be able to take this input array, add the items into the heap one by one, and get this resulting picture. Okay, great. And by the way, do you remember how we represented a heap in memory? Because this cartoon picture is great, but what was the actual implementation of a heap? Remember, we could have used all these different tree representations, but do you remember in a heap, we actually used an array to represent the heap. So that's what I'm showing here. This is the underlying representation of the heap. This is the cartoon picture. This is what Java sees. It sees an array, and the array represents the heap. That's why I'm going from one input array to another input array. That's because I threw everything in a heap. And how do I represent the heap in memory? It's an array. Okay, so there it is. I have a heap, and the max item is at the front. There it is, the 41. And then items below it are smaller. That's the heap. Okay, now it's time to take all of the items and delete them out. But I guess before I do that, I want you to tell me the runtime of just this step. So we haven't finished heap sort yet, but I'm kind of halfway there. I put all the things in the heap. So how long did this take? How many operations did I have to do with the heap, and how long did each one take? Remember your heap runtimes? So there are n things that I had to add, and how long does it take roughly to add an item into a heap with n items? Just give me a big O bound. Be lazy. What do you like? How long does it take? No takers? Yeah, I like n log n. So there's n items, and it takes log n time to insert each element into the heap. So I have a total runtime of this step of n log n. There's n items. Each one takes log n time to insert. N log n so far. I'll probably have to add some other stuff, but for now, n log n. Okay. Now it's time to delete all of the items out of the heap one by one, and I know that they'll come out in order because that's the property of a heap. You always delete and get the largest item since it's a max heap. By the way, at this point, I no longer need the input array, so I'll throw it away. You'll never see it again. I'll just use this representation of the heap, and I'll pull out items one by one, and I'll stick them in my output array. Since I'm using a max heap, I'm going to fill the array backwards, because remember, I get the largest items out first. So I'll put the largest item here, and then the next largest item here, all the way down to the smallest item in the first box or element. Okay, so here I go. I'm going to take this heap. I'm going to pull the smallest item out. And remember, when you pull the smallest item out, a bunch of stuff happens in the heap. Some stuff shuffles up and down. I don't really care what happens, but somehow things in the heap shuffled up and down. I got the 41 out, and I put it at the end of the array. And again, I don't expect you to instantly see that this is how the array changes, and this is how the cartoon picture changes. But I think if you just wrote it out, you'd be able to perform this heap operation. It's just a heap delete. I delete an item, some items sink or float, and I get the 41 out. And now the heap is smaller. See, the heap used to have 9 items. Now it has 8. So that's good too. Okay, let's keep going. So again, I go to the heap. I pull the largest thing out of the heap. happens to be 32. The items are going to shuffle around because I deleted something from the heap, and I put the 32 in the next position in the output array. And I keep going. I pull out the next thing, I pull out the next thing. And again, the exact way in which these numbers are shuffling is something that I think you could do with enough time, but it's just not interesting enough to do now. I trust that you can do the heap operations. So there we go. We pull items out one by one, and we fill them into the output array until everything is gone from the heap. Okay, that's the cartoon. Like it? Any thoughts? So again, I pull something out, and I don't care how these items shuffle. It's not my concern. That's the heap's problem. And I put the items one by one into the sorted array from the back to the front. Okay, thoughts, questions? Yeah, sorry. The question was, oh, sorry. Yeah, the question was, could I not start with the items at the end of the heap? So like start here and just add backwards, I guess? Well, the problem is that if you remember the heap property, the items in the heap are not necessarily all sorted. Property in the heap is that this item is going to be greater than both of its children. That does not necessarily mean the heap itself is sorted. And in fact, if you look at this heap, it's not actually sorted. It just has the heap property that every item is less than, or in this case, greater than its two children. And that's what makes deleting the largest item fast. That's a great question, though. So you might be tempted to just read the heap in backwards order, but you will not get a valid sort because heaps don't have to keep things in sorted order. They just have to organize things enough to make deleting largest items fast. That's a great question, though. I'd never seen someone ask that before. It's really cool. Okay. So you've now seen phase one, which was shove everything in a heap. You now saw phase two, which was delete an item from the heap over and over until it's empty. So what is the total runtime? There were two steps. We figured out the first step is theta n log n. What about the second step? How many things did I have to delete? N of them. How long did each delete take? How long does it take to delete something from the heap? Remember, if I want to delete something, I have to like take the next item, put it at the root, and do some syncing. So each delete takes log n time. So I have one step that's n log n. Then completely separately, I have another step that's n log n. So in total, I have to do one n log n step plus another n log n step. Then I sum them up, and I get a bound of n log n, which is, you'll notice, better than selection sort. So selection sort was n squared. I have now gotten it down to n log n. Pretty cool. And it was all thanks to the heap. Okay, what about memory usage? And again, we don't want to count the initial input array. That's kind of cheating. The input array is always going to be theta of n. But how much extra space did I have to use? So if I go back and I watch the entire algorithm in action, well, here was the input array. We don't count it in the extra memory. It's OK. But then I had to create this extra auxiliary array to store the heap. So I had to create another array of size n. And then I had to create another output array, third one, of size n. So in total, my extra space that I use is roughly n plus n, which is 2n, which is still theta of n. So I had a theta of n factor in terms of extra memory. It wasn't the initial array, but it was those extra two to store the heap and the output. So that's heap sort. It works. It's n log n, but there's a bit of extra memory usage. So we're going to get rid of this extra memory usage with some fancy trickery coming up next, unless you have questions. OK. So that was naive heap sort. Hopefully it didn't feel too bad. And again, I almost think that the slide's complicated a little bit more than it has to be. It really is just shove everything in a heap and delete it all back out, and things will pop out in order thanks to the heap. But now let's do in-place heap sort. And here, what I want to do is I want to avoid having to create all of those extra arrays. I don't want to make another array and then put the heap in the other array. I want to do everything in the original array just by swapping items around. So can I do that? Well, yeah, it turns out I can. So here's what I'll do. I'm going to take the original array. Here's the original array. So first of all, is it sorted? No. Was this array a heap? No. Who knows what this array was? Someone just handed me a bunch of numbers. Is this a heap? it's probably not a heap. But what if I really wanted it to be a heap? Remember, in naive heap sort, I would make a second array, and then I'd make it into a heap. I'd add all these items into the second array, and the items would shuffle around, and I get a heap. And so I look at this first array. You're not a heap, but I really wish it was a heap. So what if I made my wish come true, and I said, you are a heap? Well, if this is a heap, I can draw it out in cartoon format. And remember, this array is just the heap, is a heap implemented in Java. So it's not really a heap. I don't know what the user gave to me. But if I really wished and I wished, and my wish came true, and this was actually a heap, it would look like this, right? 32, 15, 2. I'm reading off the items in level order. That's my heap. Except, is this actually a valid max heap? No. And in fact, that's not that surprising. The user didn't give me a heap. So if I pretended it was a heap, why would it be a valid max heap? In general, it's not going to be. For example, this 15 should be greater than both of its children, but it's not, right? 15 is less than both of its children, which is wrong. So while I wished for this array to be a heap, it's not actually a valid heap. So I want to make it a valid heap. I want to take these items and shuffle them around and do some swaps so that this array becomes a valid max heap. And it turns out the way to do it, I'll tell you how to do it, and then we'll convince ourselves that it works, is I will start at the bottom, and I will scan my way up in reverse level order, and I'll sync every single node. So every single node will get sunk as far down as it can go. And if I do that, I will get a max heap after I'm done. So I'll do it, and then we'll convince ourselves that it works. But is everyone OK with the first step, which is that I get some random old array from someone else? It's not a heap, but I pretend it's a heap. And now I'm going to fix it so that it's actually a valid heap. OK, so here we go. I start at the bottom, 17. I sync it. I want it to go down to its rightful place. Well, there's nothing below it. So if I sync it, nothing happens. OK. Then I sync the next 17. What does it do? Nothing. OK, that's fine. Now we sync the 21, or the 41, sorry, nothing happens. I sync the 26, nothing happens. I hope you're having fun. I sync the 19, nothing happens, nothing happens. OK, here is where something interesting happens. I get to the 2. I'm going in reverse level order. I get to the 2, and I want it to sync. Something's going to happen because this 2 is in the wrong place. This item here should be greater than both of its children, but the 2 is not greater than both of its children. The 2 is like, I'm not cut out for this. This is too high of a position for me. So I'm going to sync to my rightful place. And it looks below itself and says 26, 41. Who would be the better boss? Well, 41's larger. So we will swap the 41 and the 2. So if you ignore the colors for a moment and just look at the picture, the 2 and the 41, they swapped places in the picture. They also swapped places in the array, which is representing this picture. And so the 2 is now sunk into its proper place. OK, let's keep going. So what do I sync next? I sync the 15 next. I'm just going in reverse level order. So I sync the 15 next. Remember, I just sunk the 2. Now I sunk the 15. And so I think this does do something, right? Because I look below, and I need to be greater than both of my children, but I'm not. So the 15's like, nope, I'm not cut out for this position. I'm going to go down, find my rightful place. And the 19 is bigger. So I'll swap myself with the 19. So the 15 and the 19, they swap. 15 and 19, they swap. Good. And finally, I get to the 32. And the 32, I want it to sync. And it looks below itself and says, 19, that's fine. But 41 is not OK. So I'll swap myself with the 41. I will look below again to see if I have to sync any further. And well, I'm greater than the 26. I'm greater than the 2. So I'm happy here. And after syncing everybody, if I look, everything is in its proper place. This is a valid heap. Every item is greater than both of its children. So are we at least OK with the mechanics of how to do it? You read the items right to left, bottom to top. You sync every item. And when you're done, I promise you, you will get a heap. That's OK? If so, I'll tell you how it works. Question so far? Why not use a min heap? Stay tuned. I promise you, you will see why the max heap is useful. Although if you wanted to, naive heap sort could have used the min heap. OK, so here we go. Let me tell you why this works. So as I sync, let's see, let me go find a place where I think this is informative. Okay, so maybe let me stop at, I want to stop at the 32 actually, at the very end. So I pause the demo right here, and I'm looking at this 32. So at this point, do you agree that the left side is a max heap? Yes, because we sunk all the items in reverse level order, so we know it's a max heap. That's the property that I want you to believe in. And what about this right subtree? Is this also a max heap? Yes, because I sunk all of the items in reverse level order. So this red subtree is also a max heap. So if you trust me that the left subtree is a max heap and the right subtree is a max heap, well then, if I take this extra item up here and I sink it, I will promise to you that the result is a max heap. And the way that I'm going to convince you is, how did I delete something from a heap? Way back like 20 lectures ago, how did I delete something from a heap? Well, remember, when I deleted something, I took the root, right? I took the root, I deleted it, I took some random item at the end, and I stuck it in the root, and I said, you need to sync to your rightful place, and after you sync, the resulting data structure will still be a heap. That's kind of the same flavor as what I'm doing here. I'm not really deleting items, but if you trust from the priority queues lecture that I can just stick any old item at the top, so I take the next item, whatever, and I say, you're the new boss, and then that boss syncs to its rightful place, and the result is a heap, well then, that's basically all that I'm doing in my heapification process. If I have a left subtree that's good, a right subtree that's good, I can stick any item up here. It could be 32, could be 45, could be a billion, could be -10, whatever item I want up here, could be anything, as long as the left and right subtrees are heaps, and I sync this item, and the resulting data structure will be a valid heap. That's the idea, and if I apply the idea inductively from the bottom all the way up, then I will see that this works fine. So kind of the base case, if you're curious, is like a 0 or a 1 item heap. The item 26 all by itself, that's a heap. And then I induct my way up using larger and larger heaps until eventually I get to the entire thing being a heap. But that's kind of the rough idea. If I sync every item, I know that my resulting data structure will be a heap because I'm going in reverse level order. Okay, so again, I think even if you didn't totally wrap your head around the proof, you would be able to do this mechanically. But are there any thoughts or opinions about the proof before I go onwards? This is probably the most annoying part of today, by the way. So, okay. Great. So we saw that syncing every item will give me, in reverse level order, will give me a heap. And I didn't have to create a new output array. That was the trick that made this so cool. I didn't have to go and create a second output array and put all the items into a new heap. I just took the original input array, pretended it was a heap, I wished it was a heap, and the items are not in the right place. Then I did some syncing to swap all the items until the resulting data structure was a heap, and it is now. Okay. Great. So everything is heapified, and I didn't have to use extra space, which is cool. So now it's time to do the same process as before, which is delete items from the heap. Every time I delete, some things will shuffle around, and that's OK. And I will shove the result into my output array. So I could do that, and I'll go back and show you. Let's go find it. Sorry, this lecture has so many slides. Let's see. OK, heap deletion. Where are you? Here. So I could do what I did from before, which is I had my valid heap, and I deleted the items, and I put them in the output array. But that would require creating an extra output array, which is extra space. And I don't like extra space. So while I could do that, and this is the place, by the way, where the max heap is finally going to be useful. I could have done all this with the min heap until this point. Now the max heap trick is going to come in handy. So like watch just the green elements of the heap. As I delete things, the green is like draining out. So look, the green was, everything was being used in the heap. And as I deleted items, just focus on the green, is draining away. And then the array is starting to get less and less used. Now, watch the output array. Maybe you see where this is going. Right now, the output array is totally unused. But I start to fill items. Like watch the gray. It's filling in from right to left. So maybe you see the trick that I'm about to play. If the heap is draining items such that its back elements are starting to become unused, and the output array is filling in items from the back such that they're starting to get used, well, maybe you see the trick now. Maybe I don't need 2 arrays after all. And that's the trick that's going to make in-place heap sort not use extra memory. So here we go. This 41, I'm going to delete it. But instead of putting it in a brand new output array, which would be extra space, I'm just going to shove it at the end of the array. And that's OK, because the heap has vacated this element of the array. It's no longer using this part of the array, so I'm safe to put the output here. Then I take the next element, 32, and I delete it. And when I delete it, the heap's going to shuffle around, but this last box is going to no longer be used by the heap because I deleted something out, so I can put the 32 in there. Then I take the 26, I delete it, and I put it where? Right there, right? And I do the same process over and over, and eventually everything will become sorted. So it's a little bit harder to stare at, and it's not as simple as swapping. So don't get tempted to just swap the 41 and the 17. That will not work. You have to delete the item, let the heap shuffle and sync its items around, and then put the 41 in the spot vacated by the heap. And I almost think the in-place animation is kind of helpful to see what's going on here. So again, you watch the heap at the top drain, and then watch the output at the bottom fill up. That's what makes in-place heapification work. And it avoids having to create a second output array. It's pretty cool. You could try doing this with a min heap, but it would be more annoying. That's why I like using a max heap, because the items fill in from the back instead of the front. That's the one place where the max heap is useful. Thoughts, questions? Are your minds blown by this? OK. Good. That's heap sort. Let's think about runtime, and then we probably have to go. So runtime. Well, here are the things we had to do. We had to do that bottom-up heapification thing, which was sync all the items in reverse level order. And then I had to remove the largest item over and over again, just like in regular naive heap sort. So let's think about both of these steps, and then we'll add them together because I did both steps separately. So how long did it take to do bottom-up heapification? And be lazy. Give me a big O bound that you think feels right. And it might not be tight, might not be the best bound that you can give, but be lazy, give me something that you think makes sense. So if I want to sync every item, that's not what I want. If I want to sync every item, how many items do I have to sync? And in the worst case, give me an upper bound of how long each sync takes. So I have to sync everything, right? I have to sync everything one by one. And in the worst case, give me an upper bound for how long each sync takes. If I start at the top and I sync all the way down, log n. So I have n things to sync. Everything takes log n. So I at least have an upper bound of big O of n log n for the bottom-up heapification step. And then what about that second step? It was the same thing as before, which was I take every item and I remove it. There are n items to remove. Every removal costs me log n. So in total, the removal is n log n. So I have one step that's n log n. I have another step that's n log n. I add them together, and the time complexity is still n log n. But I got rid of all that extra memory. So the space complexity would be theta of 1, because it did not have to create any extra array. The extra space that I need was not scaling with the size of my input. OK, so that was heap sort. And I guess before I let you go, I want to show you something that I think people always ask me about. And I realize that this is a nice place to show it to you. So people always ask, what is the difference between big O and worst case? I know you've had this question, so I'm going to try and finally answer it for you. So what if I told you that our analysis, that bottom-up heapification was n log n, was actually pretty lazy. So we just said there's n things to sync, and each sync takes log n in the worst case. And I multiply them together, and I get n log n. And I used big O. Why did I use big O? Because I said, well, I know it's n log n or better, but I actually don't know if it's exactly n log n. If I knew that it was exactly n log n to sync all the items, I put a theta here. But I put an O here because I'm lazy, and I actually don't know if this is the exact best runtime. In other words, I don't know if this bound is tight. And it turns out, if you really go and play with the math, and you get a really funky summation and you sum it out, it turns out that bottom-up heapification is actually not n log n exactly. It's actually theta of n. And it's not something that I expect you to see right away, but turns out if you do the analysis, it's theta of n. Does that mean that our analysis was totally busted? Well, not really, because here I said bottom-up heapification is big O of n log n. And what I was really saying was bottom-up heapification, the thing where I sync all the elements, it's n log n or better. Is it exactly n log n? I don't know. Is it better than n log n? Maybe. But I know that it's not going to be worse than n log n. That's where I use the big O notation. But it's not the same thing as saying it's n log n in the worst case. It turns out it's actually not n log n in the worst case. It's actually theta of n in the worst case, if you do really careful analysis. So here is a case where I used big O to be lazy in my analysis, and it turns out that is not the same thing as worst case. The worst case was really theta of n. But I was lazy and I bounded it by saying it's n log n, maybe it's better, who knows. But here's a case where it's not, where big O and worst case are not the same thing. So now you know. And by the way, why was I okay by using this lazy analysis? Because let's say I really did find out, oh shoot, this is actually theta of n time. Would that change the runtime of in-place heap sort? Well, not really, because I have a theta of n step. Then I have a theta of n log n step, and if I add them together, the resulting time complexity is still n log n. So that's why being a little bit lazy here turned out to pay off. Doesn't always pay off, but in this case, it did. And I used a bound that was not totally tight. So now you know all about big O and worst case. So I snuck that in there. So you saw two sorts, but I know you're not satisfied. So come back next time. You will get more sorts. Let's answer some questions on Zoom while you all like squeaking your chairs and head out. So questions. Let's see. Why is the max heap better than the min heap? It's because I wanted to do that in place operation. So the max heap is better because it allows me to do this thing where I can delete something and fill it into the back. That's why the max heap was better. For in place heap sort, the textbook says that bottom up construction is theta of n. Shouldn't it be n log n? That was the thing that we just talked about, which is that I set n log n as a big O bound to say it's n log n or better. But it turns out I can actually get it all the way down to theta of n, but I just upper bounded it lazily with big O of n log n. And the question of why is it n log n? It's because I have n items to sync, and in the worst case, every sync could take log n. If I have to sync all the way from the top to the bottom, there are n items, every sync takes log n time. So my upper bound, which turned out not to be exact, but was a good upper estimate, was n log n. Okay, those are all the questions on Zoom. So goodbye, Zoom.